Welcome everyone to RStudio workshop series number 4. Today we are working on correlations. I'm going to show you two kinds of correlation today. A little bit of backstory before we get started. A lot of these stats you might have been taught if you've ever taken a statistics class, they require what's called normality, which is a fancy way of saying the data has to look a certain way for us to be able to use that test. So if you've ever done a correlational test before, it might have been the parametric test, i.e. the test that requires normality. That's the Pearson correlation. If you do not meet normality, we'll cover this as well today, we can instead do what's called the Spearman correlation. So let us begin. Pearson correlation. A Pearson correlation is used to determine the strength and direction of a relationship between two continuous variables. And like I've already hinted at, this test is parametric, which means it assumes the normal distribution. It assumes normality. Biggest amount of data in the middle, smallest amount of data at the ends. I've left you some links in the document today to help you run a Pearson correlation. I'm going to show you how to do it start to finish. The first thing we have to remember to do before we open anything on our computer is to set our working directory. We have to tell our computer where are we working on our computer. We can do that by clicking Session, Set Working Directory, Choose Directory. So by clicking Session, Set Working Directory, Choose Directory, this will open your File Explorer so you can point to where you have put the downloaded files for today's workshop. So if I do this, it will show me my File Explorer. I'm in Documents, Classes and Workshops, Lindsay's Workshops, Micro Workshops, RStudio. I don't see anything in this file folder, but I know I'm in the correct location, so I can click Open. This will give me my code in the bottom left-hand corner in our console. This says set WD left bracket to say this is a function. It's a set working directory function, and it has the very long link to where I am working on my computer. Hopefully yours is a little shorter. What you have to remember to do if you're here at today's workshop or watching the recording is take this function, not including the blue Pac-Man at the front, that greater than symbol, and you want to copy and paste it onto line 23. So that if you come back next, let's say tomorrow or next week, and you wanted to try to run this code, it's going to point to your folder structure on your computer. So we set our working directory. Now we would like to open our file to do work in that file. We can open many different files on RStudio. The file type we're going to open today is what we call a CSV file or a comma delimited file. To open a CSV file on RStudio, we can use the read.csv function. Within that function, what we have to remember to do is give the exact name of the file as written with the file extension within quotation marks. So my part of the code, I've given it a name. I've called it fake_data is equal to read.csv left bracket quotation mark capital F fake underscore capital D data dot CSV end quotation mark end parentheses. You have to spell the file exactly right, and you have to have remembered to set your working directory or else the file will not open. So if I highlight line 25 and I click run, I get blue text down in the bottom left in my console showing that this worked. In the top right, I now have a data set called fake_data, which has 30 observations of 7 variables. So we've opened our file. That's step 1. Now we can actually start to do things with this file. Every test that we try to do has certain assumptions or certain rules that must be met in order for the results of the test to be valid. So there are multiple different rules for different kinds of tests, and we're going to cover all of them today. The first assumption for running a Pearson correlation is that you have two continuous variables. And we talked about continuous variables a few weeks ago. There's a common package we can use to review our data to make sure we actually have continuous variables. So if you have not come to one of my workshops before, you will need to highlight and run line 30, which is install.packages left bracket quotation mark tidyverse end quotation mark end bracket. What this does is it will take the tidyverse package. Someone else has created this package with different functions. It will take it from the internet and put it on your computer so that you can use the functions within that package. I already have tidyverse on my computer. I don't need to run line 30. You can run it again if you already have it, but you don't need to. I'm instead going to highlight line 31, which is library left bracket tidyverse end bracket. When I run this, I get some text down in my console, and it's worked. What this means is it has loaded tidyverse for me. I don't have red text saying that there's a problem, so this has worked appropriately. I can now use the functions within tidyverse to look at my data. So let's do that. We're going to take a look at or take a glimpse of the data set that we have open in RStudio. So we can use the function glimpse, which is glimpse left bracket, capital F fake underscore capital D data, because that's what we called our data set. So I can highlight this and I can click run, and it will show me my data in the bottom left in our console. It says we have 30 rows and 7 columns, which is good because that matches what's in the global environment in the top right. And it's got $sign to say, here's a different column for you. So we've got $sign gender, which is listed as INT or integer data. The data we're going to use is $sign fake data 1, which is listed as DBL or double, which is RStudio's way of saying continuous. And we're also going to use $sign fake data 2, which is a different column in our data set, which is also listed as DBL or double, which is RStudio's way of saying continuous data. So what this means is we have met this assumption. Our data is considered continuous because we're going to use the fake data 1 column and the fake data 2 column. Another way to do this, which I don't have in the slides or in the script for you, is you can just double click on fake data and it will open it like it's an Excel spreadsheet directly within RStudio. And you can look at your variables and see what's going on here. So you could do the glimpse function to look across and it will tell you the data types listed. You could also look at your data and say, what kind of data do I have here? In fake data 1, I've got a range of values. I've got a bunch of decimals. That looks continuous. The glimpse function helps us double check that RStudio has appropriately put the correct data type on that column of data. So because we've got DBL, which is RStudio's way of saying continuous data, we get our check mark, we're good to go. We've just finished assumption 1. We checked to make sure that we've got the correct data type for our variables. We've got 2 continuous variables, which means we've passed that assumption. We're allowed to move on. Assumption number 2, we should have what's called a linear relationship between our 2 continuous variables. There are many ways to check linearity. The easiest way is we can just make a scatter plot. We can do what's called visual inspection. We can plot one thing on the X, one thing on the Y, and just have a look at it and say, does it look kind of like a line? So there's lots of different ways to make plots and really fancy, really pretty plots in RStudio. I'm just showing you the most basic way to do this on line 39. We're literally going to use the plot function. We're going to say fake data, $sign fake data 2 to say plot fake data 2, that variable. And we're going to give it a comma and say fake data, $sign fake data 1 to say we'd also like to plot fake data 1. We'd like to plot that variable. So if we highlight and run line 39, mine gave me some red text in the console because my plots package is itty bitty right now because I was working on something else. So if I just make this bigger and run this again, it should show up. Boom. Sometimes the graphs down here are a little hard to look at. They're a little hard to see. So you can click the zoom button, which will make it full size so you can look at things a little bit better. And what we're looking for here is, it doesn't have to be perfect. It doesn't have to be exactly a straight line, but you're looking to see, does this kind of look like a straight line? Is it either like going flat across the page? Is it going up to the right? Is it going down to the right? Doesn't really matter the shape of it as long as it looks roughly like a straight line. Here we might actually have a little bit of a problem because if I sort of cut this graph in half, what we see is the left half of the graph looks like it's going down to the right. And the right half of the graph looks like it's going up to the right, which is a fancy way of saying we kind of have this V or U shape going on. And if you've ever taken like a high school math class, you might know that that's generally not considered a straight line. That's some kind of quadratic. So in this case, we might not have passed this assumption. Just by visual inspection alone, it looks like we might not have a straight line going on. So it's important to always check your assumptions because if we didn't check this assumption, we wouldn't know that maybe it's inappropriate to use this test because it doesn't look like we have a line here. Today, we're just going to pretend it's a perfectly straight line. We're going to do the test anyway, but it's a reminder to always check your assumptions. All right, I'll make this so we can see things again. So we finished assumption 2. Our data doesn't look fully linear, but we're going to keep going today and pretend it looks okay. The next thing we have to do is check what's called assumption 3. Each variable, so both fake data 1 and fake data 2, should be approximately normally distributed, i.e. this is the parametric part of this test. This is normality. There are several ways to check normality. I'm going to show you the statistics version. So depending on how big your data set is, how many observations you have per condition, there are two different statistics that we generally use. One is called the Shapiro-Wilk statistic if we have fewer than 50 observations. And if we have 50, talking is hard today. If we have more than 50 observations per group, we would normally use what's called the Konglomerov-Smirnov statistic. So we have pretty small groups today. We've got 30 per group, so we're going to use the Shapiro-Wilk statistic to check normality. The way we do this is we use the Shapiro.test function. And within that function, we have to give it the name of the data set, so fake_data. We give it a $sign, and then we give it the name of one of the variables. And we have to run this twice because they both need to pass normality or we can't use this test. So I can actually highlight both of these at the same time, and I can click run. And I can get the output from both of them at the same time. So for fake data 1, it says Shapiro-Wilk normality test. It tells you which data you used. It gives you your statistic, and it gives you a p-value. The p-value for fake data 1 is 0.4551. Because this is an assumption check, if p is greater than 0.05, we get our check mark, our green light. We have passed normality for fake data 1. We also need to check fake data 2, so that's just a little bit lower. It says Shapiro-Wilk. It tells you which data set you used. It gives you your statistic, and it gives you your p-value. And here we have p is equal to 0.002933. This is less than 0.05, which means we have failed normality. We had a big red X. We had a stoplight. We say something is wrong. We cannot use this test. It would be inappropriate to use this test because we did not pass the normality assumption, which means you would then switch to the non-parametric test or the non-parametric correlation, which is called the Spearman correlation. We're going to run both today. We're going to pretend that it worked and run the Pearson, and then we'll also run the Spearman. So here, because one of our tests has failed normality, we say the entire thing has failed. Both need to pass in order for us to be able to run this test. The next assumption, assumption 4, is no significant outliers for each variable. So for both fake data 1 and fake data 2. I haven't left us any code for this today because different fields or areas of study have different ways of checking for outliers, including things like visual inspection using box plots, or doing things with like the mean and standard deviation. So I've left you some text there if you are running this on your own data. So if you are part of a research team and you need to remove outliers, you definitely want to check for those. You want to chat with your research team about how that is done in your lab or in your field. If you have removed outliers, you then can rerun your other assumptions. So things like linearity, things like normality, and sometimes removing outliers can actually fix normality. So in our example, normality is broken for one of our 2 tests. If we were to remove outliers and check again, we might find normality is okay, which means we're allowed to use this test. So always check that. All right, so we've finished checking our assumptions. Now we can actually run the test. This is the part that actually doesn't take very long. The assumptions generally take a little bit longer than running the test, but it's really important that we're checking those assumptions because like I just said, if you failed one or more assumptions, you probably can't use the test you're trying to run and you might have to switch to a different test. So if we're actually trying to run the Pearson correlation today, we're going to check the strength and direction of the relationship between fake data 1 and fake data 2. It's all fake data. They could be whatever you want. It could be, I don't know, let's see if height impacts your happiness. Like, that would be a silly question. But we can ask different questions to see what's the strength and direction of that relationship. That's what we're doing with the Pearson correlation. We're going to use the core.test function. And if we don't know what that does, we can highlight line 68, which is !core.test. And what this will do is it will give us down in the help window the RStudio documentation for what this test actually does. So core.test is from the stats package, which we've loaded from tidyverse. And it says test for association/correlation between paired samples. Description: test for association between paired samples using one of Pearson's product moment correlation coefficient, Kendall's tau, or Spearman's rho. Those are all very statsy symbols. You don't have to know those. So it's a fancy way of saying you can use core.test for 3 different things. Today we're going to use it for the Pearson correlation. So how do we actually do that? All we have to do is give it the name of the test we want to run, the Pearson, and give it the 2 variables we're trying to use. So let's review this together. On line 70, we've got core.test, left bracket, capital F fake _ capital D data, $, capital F fake _ capital D data 1, comma, capital F fake underscore capital D data $, capital F fake underscore capital D data 2, comma, method equal sign, quotation mark, Pearson all in lowercase, end quotation mark, end bracket. That's the function we're using, which is to say we're going to do a correlation test. In our fake data set, we're going to compare fake data 1 to fake data 2 using a Pearson correlation. So we can click run. And in the bottom left, it will tell us exactly what we just did. It will give us in blue text the code we ran. And then in black text, it will give us the actual result of that test. So we've got Pearson's product moment correlation. It gives you the data. So we've run fake data 1 versus fake data 2. It gives you a t-value, your degrees of freedom, and a p-value. Our p-value here is 0.6373, non-significant because this is greater than 0.05. It says alternative hypothesis, true correlation is not equal to 0. It gives us a 95% confidence interval, and it gives us some sample estimates as well. So in inferential statistics, the main thing most people tend to care about is the p-value. So here we have a non-significant correlation, which is a fancy way of saying we fail to be able to say whether there is some sort of relationship or association here. And if we go back to our plots for a second, because we've already plotted our scatter plot, I can zoom in on this. That kind of makes sense. We don't have a very tight cluster of dots along a very obvious line. So it also, reminder, it doesn't make sense to run this test because this doesn't look particularly linear. We've got more of like a U shape or a V shape, which is quadratic, not a line. So it makes sense that this test isn't really working as expected because we failed that assumption. So it's saying we can't really say that there's an association here. We don't have a tight cluster of lines going up in one direction, for example. So that makes sense. And that is how you run the Pearson correlation, which is the parametric correlation. It assumes normality, and we broke normality for one of our two pieces.